Okay, welcome back to Calculus 1. This will be the 7th lecture of the course. In this lecture, we're going to get into basic differentiation. So we'll talk specifically about many of the rules for identifying derivative functions. And this will, so contrast that with what we went through previously, where we used the definition of the derivative to identify our derivative functions, which if you do a few of those examples, you'll discover, wow, this is kind of the long way around, isn't it? Indeed it is. And so obviously a lot of work has been done by mathematicians to figure out quicker ways to identify the derivative function. And that's what we're going to get into this time. So we'll call this 2.2. Basic differentiation. And I think I'll put on the end here rules, because that's going to be kind of the focus of this section. So what are the differentiation rules that I can use to identify derivatives? So previously we used the limit definition, right? So remember, the limit definition said that the limit as delta x goes to 0 of f of x plus delta x minus f of x, right, all divided by that delta x variable. So that was gonna be the definition of the derivative. So given an f of x, you can plug in x plus delta x and calculate the difference, and then ratio that by the change in x, that delta x feature, and then look at that ratio, this difference function, as delta x goes to 0. And the result would be the derivative function. So in this section, we're going to pivot off of that, and we're going to focus in on some of the rules that can be used to identify derivatives now that we've been through this exercise a few times. So let's start with the theorem. So we're going to let c be a real number. Then here's the story. The derivative of a constant c is equal to 0, irregardless of the constant. Okay, so this is the first derivative differentiation rule that we'll talk about. Let's go ahead and prove this one because it's simple, and we want to think of Calculus 1 as a not exactly a testing ground for proofs, but a nice place to sort of introduce the idea of proofs. Certainly I don't know of any Calculus 1 courses that would require you proving theorems, but it is a nice place where frequently instructors will make use of some of these theorems to demonstrate the idea of a proof. And so let's go ahead and prove this one. And so here we'll use the definition of the derivative. So the derivative of a constant c with respect to x, well, let's just plug in that definition. Delta x going to 0, that limit, and then it's f of x. Sorry, f of x plus delta x minus f of x, all divided by delta x. Okay, now we can plug in our constant, right? So the function here, f of x, is just c, right? So f of x plus delta x is still just c. So the limit as delta x goes to 0 of c. Now what is f of x? It's the same thing, right? Looks like that. Okay, and so then that means we have the limit as delta x goes to 0 of c minus c, which is 0 over delta x. And so the implication here is that this ratio is 0 irregardless of the value of delta x. And so this would be the limit as delta x goes to 0 of 0, which is naturally 0. Okay, and so that's a simple, straightforward proof of this initial basic differentiation rule. Okay, let's take a look at another one, slightly more complex, obviously far more complex actually. Let's jump to this. So we're going to let n be any rational number, okay, n is a rational number, then the derivative of x to the n is equal to n times x to the n minus 1. So this is one we've seen, right? We've done a number of examples with polynomials where we've differentiated polynomials. And so this is an extremely valuable one. Any variable x raised to the nth power, where n is any rational number, can be easily differentiated using this form. So let's go ahead and prove this one too. We won't prove all of the ones that we discussed today, but this is a good one to look at. It's a little more complex than the prior, but certainly within the scope of this class. So the derivative of x to the n with respect to x, again plugging in the definition, is x plus delta x to the n power minus x to the n, all divided by delta x. Okay, now this thing here can be expanded. Okay, and so it might take a little bit of effort, but if you kind of start with looking at like x plus delta x squared and then x plus delta x cubed, you'll get that there's a pattern to how this expansion works. Okay, and what you end up with is something that looks like this: x to the n plus nx to the n minus 1 times delta x plus n minus 1 x to the n minus 2 over 2 times delta x squared, and so on, right? And then ultimately at the very end of this piece here, you're going to have a delta x to the nth power. That's at the end of this expansion. And then after that, of course, minus x to the n. Let's not forget that. Okay, now that whole thing is divided by delta x. Okay. Now, that expression cleans up nicely. And basically, what you can do is you can divide out these delta x's, and what you end up with is the limit as delta x goes to 0 of nx to the n minus 1 plus n minus 1 x to the n minus 2 times delta x. Okay, and then that's all over 2. That's this term. Comes down here. Plus, and then again, take some time to think this through. You would get delta x to the n minus 1. And then, of course, this leading term here cancels with the prior term, the term at the end. Right? And now what you'll notice here is that every term in this expansion has a delta x in it. Right? So you see one here. You see all of the terms beyond this would be, the next term would have delta x squared, and then delta x cubed, and so on, until the final term would be just delta x to the n minus 1. Except this leading term here is the only term in this expansion of this guy here that doesn't have a delta x in it. And so naturally, what's going to happen when delta x approaches 0? This guy's going to 0, that guy's going to 0. All of the terms in the expansion go to 0 except for this one, right? And that's where you get your derivative from. So the derivative of x to the n is equal to n times x to the n minus 1. Okay. Now, something to notice. Many watching this may notice this. This proof really only works when n is a positive integer greater than 1. Okay, so when n is a positive integer greater than 1. Now, for the case when n is less than 1, or whenever n is a rational number, not an integer, it's somewhat more involved, right? It's somewhat more involved, but it's going to follow the same basic format, right? You're going to be able to expand this thing, cancel a bunch of stuff. It's going to follow the same format in the sense that you're going to use the definition, expand some stuff, algebraically reduce everything, and then take the limit and be left with this term here. Okay, so it's a bit more involved. I encourage everybody to try to figure it out in the case when n is not a positive integer, but it's going to follow this same basic format. Okay, let's take a look at a few examples, as we've got some theorems in front of us now. So let's take a look at a few examples. Let's differentiate f of x equals x cubed. Okay, so previously we would have used the definition. We would have plugged in the difference quotient, taken the limit as delta x goes to 0. But now what we can do is we can simply say that f prime of x cubed, f prime of x is equal to the derivative with respect to x of x cubed, which according to the formula is just n is 3, bring that down front, and then it's reduce the exponent by 1. So 3 minus 1, I'll put it in there just so people can see. So that's 3x squared. Okay, so it's just that easy. And so it's basically a one-stepper. You can look at this, and if you remember the form, you'll know that that's 3x squared when you differentiate. What about another example? Let's say g of x equals the cube root of x. Okay, so something to note here is that, so f prime of x, sorry, g prime of x is equal to dx of the cube root of x, right? Now, another way to think about the cube root of x is that it is x to the 1/3 power. Okay, so if you weren't aware of that, dig open your pre-calc book and make sure that you understand that. But the cube root is the same as the 1/3 exponent. Okay, so then we can just apply the formula, and so we'll see that it's 1/3 times x, and then it's 1/3 minus 1, which gets us 1/3 x, and then a third minus 1 would be -2/3. Okay. And so we can clean this up a bit. This would be better written as 1 over 3x to the 2/3 power. That's the derivative in this case of the cube root of x. Okay. Very good. How about another example? What about something like this? What if I have y equals 1 over x squared? What's y prime? Okay, so you should notice here that 1 over x squared is the same as x to the -2 power. Okay. So if y is equal to x to the -2 power, then we can calculate the derivative, dy dx. That's just going to be equal to d dx of x to the -2 power. So again, hopefully the notation is coming along for people. I try to be real explicit with the notation at this stage in the course. So dy dx is the derivative of y with respect to x, and then I can write d dx, and then instead of the y I can plug in the actual function, right, this piece of it, right? So y is equal to x to the -2, so that's what's happening here to here. Okay, and then I can just apply that formula. So in this case n is -2, so I bring that down front, and it becomes x to the -2 minus 1. And so I get -2x to the -3 power, okay, which is better written as -2 over x cubed. So really quick, 3 nice examples of differentiation that are making use of these rules that greatly accelerate the pace at which you can calculate these things. Let's take a look at another example, something a bit more involved perhaps. Find the slope of the graph of f of x equals x to the 4th when x is equal to 1. Okay, so let's calculate the derivative first. We're talking about the slope of the graph. So f of x equals x to the fourth. That implies that f prime of x is equal to 4x cubed. Okay, so again, n is 4. Bring the 4 down front, and then it's n minus 1. So it's the third power. So remember, f prime tells us the slope of f at any point x, right? And so we want to know the slope of the graph at x equals 1. So that means f prime of 1 would be equal to 4 times 1 to the third power, which of course is 4. So there we go. Another example. Again, this would be quite involved if you had to calculate the derivative using the definition. But the fact that we can just use this quick differentiation rule makes everything much simpler, much quicker. It's still just complicated underneath the hood, but it's simple on the surface. Okay, how about another example? Examples are the king when it comes to this stuff. Let's find an equation. So similar to last problem, but let's find the full equation. Find an equation of the tangent line to the graph at, I guess I should say first, of f of x equals x squared at x equals -2. Okay, so let's just think about what this is saying. We know x squared looks like that, right? And x equals -2 is over here. There's going to be some line that's tangent at that point. We want to know what is this equation for that line. We know the form, of course, is y equals mx plus b. We need to figure out the m and the b in this case. Well, first we're going to need that slope, so that means we're going to need to calculate the derivative of the quadratic function here. And we can do that really quickly. F prime of x is equal to 2x, right? Bring down the 2, n is equal to 2, bring the n down front, and then it's n minus 1, which is 2 minus 1 is 1. So you just get 2x. All right. What's the slope? So m here, in this case, we're interested in m at -2. X equals -2, so we can plug that in, f prime of -2, and that's just as simple as doing that, right? And of course, the slope is -4. So that means our equation is y equals -4x plus b. Well, how do we figure out what b is? Well, we need to plug in a value for x and y that is on the graph of the tangent line. Okay, so, well, we know that the point x equals -2 is on the tangent line here. So what else is on? What's the y coordinate then? So f of -2 is equal to -2 squared, which is 4. So what that implies is that the point -2, 4 is on the tangent line. All right, and we can use that fact and the fact that we know the slope now to figure out what b is. So y equals -4x plus b. Okay, so we can plug in these coordinates into this, and we get 4 equals -4 times -2 plus b. Okay, so that means 4 is equal to 8 plus b, which implies that b is equal to 4 minus 8, or -4. All right, and so all of that information together with the slope means that y equals -4x minus 4 is the equation of the line that is tangent to y equals x squared at x equals -2. Okay, so a lot of words there, but make sure that's clear. All right, so we're saying I want to know the line that cuts through this parabola at exactly x equals -2. And I want to know the equation of that line, right? And to do that, I need the slope, which means I need the derivative of x squared. All right, I can find the slope easily. Then I need to do some substitution to figure out what the y-intercept in the y equals mx plus b form is. And I can do that easily as well. And so there's your answer. Very good. Okay, good. So these are some nice examples making use of the first couple of rules. Let's take a look at another theorem. So in this we'll say if f is a differentiable function, okay, f is a differentiable function, and c is a real number, then the following. So the derivative of a constant times a function, f, is equal to c times f prime of x. So what is this saying? Well, what it's saying is that if I have a function f that's differentiable and I multiply it by a constant, then the derivative of the constant times the function is the same thing as the constant times the derivative, right? So basically what you can kind of think of this as, and what people generally think of it as, is the following. If you start with something like this, then it's fine for me to pull the constant out and differentiate just the function. Okay. So that's the idea behind this theorem. Okay, let's go ahead and prove this one. Okay, so we'll prove this. Hold on, let me make sure that's focused. Let's make sure that's focused. Okay, looks good. So the proof, that's a one-liner. So the derivative of c times f of x, well, that's going to be equal to, just using the definition, the limit as delta x goes to 0 of c times f of x plus delta x, okay, minus c times f of x, of course, and then it's delta x in the denominator as per usual. Hey, now look, I've got a constant in both of the terms of the numerator. I can factor that out like this. Right, no problem. And a constant, we know when we're talking about limits, we know that a constant times a function, the limit, you can pull the constant outside of the limit. So we can pull the constant out like so. And we're just left with the usual here, which is obviously just that. Okay. So the fact that this works depends on the fact that, you know, limits have this property where you can pull a constant outside of a limit and then multiply afterwards, right? And so the derivative, that feature extends to the derivative by way of the fact that a derivative is based on a limit. All right. So this, you know, so I already said this, but I'll write it down again. This is basically, the way of thinking about this is that you can factor constants out of a derivative before you calculate the derivative. All right. So if I go like this, that's equal to c times d dx of f of x. Sometimes that's helpful to do. Sometimes it's not. Sometimes it is. And so that's the case. Now this also works naturally when you have something like this, right? Because you can just think of that, of course, as 1 over c times f of x, right? So if you think about that in this sense, it's the same thing. And so you can pull that out and then calculate the derivative of just f. And so you get 1 over c times f prime of x. Or, you know, if you wanted to, you could write this as f prime of x over c. So if your denominator is all a constant, you can just differentiate the numerator. Okay, excellent. Let's do a few examples using this, just to make sure we're crystal clear on this one. What if I start with y equals 2 over x, and I want to differentiate that? Well, he would say that dy over dx is equal to, d dx of 2 over x, the derivative of 2 over x. And I can pull that 2 outside, like so. And technically I would have this. And I think I let slip just what I'm about to do, but you can bring that x to the negative 1 into the numerator. And then you can really easily just use the fact that this is like an x to the n. So it'd be negative 1x to the n minus 1, so it'd be negative 2, right? And there you have it. So you can clean that up, I guess. You can put a negative 2, negative 1 times 2 is negative 2, and then x squared down below. All right, so there's that one. How about another example? Let's try f of t equals 4t squared over 5. So here we've got kind of a ratio in the front. All right, so then f prime of t would be equal to, you can say d dt of 4t squared over 5. And again, I'm using notation that's very specific here. You can pull that out just because I want to emphasize that that's what's being done here. That's sort of the emphasis of the section. All right, so the constant come outside, and then you just have 4/5, and it's 2t, right? So it'd be 2 minus 1 in the numerator, or in the exponent. And so this would be 8/5 t. So that's your derivative in this example. Okay. All right, how about a few more? We just want to make sure we exhaust. We're not going to exhaust the examples, of course, but we want to make sure we go through enough of these that it's clear. How about y equals 2 times the square root of x? All right, so that means dy over dx is equal to d dx of 2 square root of x, of course. You can pull the 2 out. And at the same time, we can recognize that the square root of x is just x to the 1/2 power. Right, and so that derivative would be, so 1/2 x to the negative 1/2, wouldn't it? Yep, and the 2 and the 1/2 would cancel out, and so I would be left with just 1 over x to the 1/2, which is 1 over the square root of x. All right. Very good. And let's try one more here. Maybe, let's say y is equal to 1 divided by 2, and then it's the cube root of x squared, so kind of a more complicated one. Let's see what we can do with this. Okay, so then dy dx is equal to d dx of 1 over twice the cube root of x squared. So of course we can pull the 1/2 out. Okay, and here's where you got to be a little bit careful, like come off to the side here. So you've got the cubed root of x squared. Well, what is that really? That's x squared to the 1/3 power, and you multiply there, and so that's really x to the 2/3 power, right? So that fact is going to help us a lot here, x to the 2/3 power, like that. And then I'd really want to bring that up to the top, so I can bring that x into the numerator by making the exponent negative, and I would get something like this. All right, and then I can easily differentiate that, right? All right, so it'd be negative 2/3 x, and then it's n minus 1. So let's just write it in there so we're careful here. Negative 2/3 minus 1, which would be minus 3/3. All right. And what do we get there? Well, we got the half outside, and we got the negative 2/3. And then this exponent is really just negative 5/3, right? Yep, and then the 2's cancel, and so I get negative 1/3 x to the negative 5/3. And I think we should probably write that as negative 1 divided by 3x to the 5/3 power. All right. Very good. And of course, you could convert that further. I don't know if you'd want to necessarily, but you could write negative 1 times 3, and then this would be the cubed root of x to the 5th. If you wanted to convert that, you could. Sorry. You could do that. I think this would be probably a good place to pause on that. Okay, great. So we've seen lots of examples of using of differentiating expressions that have an x to the n sort of structure, and also expressions that have a constant times something like that, like an x to the n. So let's take a look at another theorem that's really useful. So here we're going to start adding and subtracting functions. So let's let f and g be differentiable functions. Then here's what you get. So if I add f and g, the derivative, so it's like this, f of x plus g of x. Well, that's just f prime of x plus g prime of x. And if I subtract them, it's the same. Okay. Oops. Get that up there. Sorry about that. All right, so if I add them, if I've got two functions added together and I differentiate them, it's the same as adding together the derivatives. And if I subtract them, the same thing holds. So you can think of it kind of like this. This is useful in a lot of ways. Here's one of the ways that it's most frequently used. If I've got some larger function that can be broken down into the sum of two functions, then it's possible for me to do this. Right, so I can differentiate each of them separately and then add the results together. Okay, and the same thing is true of the difference there. So how about an example? This is where we can start building polynomials. So let's say g of x equals negative 1/2 x to the 4th plus 3x cubed minus 2x. Let's say I want to find g prime of x. Okay, we want to find g prime of x. Well, g prime of x is equal to the derivative with respect to x of this thing, so I'll just write it all out here. Okay, now this is the sum and or difference of three terms, right? And so that means using the previous theorem, I can just break this apart, right? So I get the derivative with respect to x of negative 1/2 x to the 4th plus the derivative with respect to x of 3x cubed minus the derivative with respect to x of 2x. Just like that, right? I can break it all apart. Now, it turns out each of these terms has a constant in front. So, again, I can pull those constants out. And again, you wouldn't have to explicitly do all of these three steps, meaning you wouldn't have to write them all out. I'm doing that because I want it to be very transparent what the mechanism is that I'm using. But you wouldn't have to do it this way. You could be a little more, you could be a little quicker and kind of cut to the chase if you wanted to. But I always recommend you do it like this when you're learning. It just makes it clearer, more intentional, like what you're up to, right? And then of course there's always time to cut corners and do things in a quicker way. once you get more practiced. But then it's a straightforward, once you've done this, it's a straightforward application of the derivative of x to the n, right? That first rule. So you get 1/2 times 4x cubed plus 3 times 3x squared minus 2 times, now what happens here with the x? So technically the exponent on this is 1, right? So I'd bring a 1 down, and then I'd go 1 minus 1, which would be 0. So the x to the 0 power is what we would end up with here, 1x to the 0 power, which is just 1. All right, x to the, anything raised to the 0 power is 1. So that's what you end up with. And we could quickly simplify this down into 2x cubed plus 9x squared minus 2. All right, so that's a very quick and easy example. All right, wouldn't have been so quick and easy if we didn't have these lovely rules. Okay, so let's do a couple more examples. This will be a video that I end up, or this will be a lecture that I end up breaking into 2 videos just due to the length. And so let's do another example here. Actually, no, let's do another theorem. Let's jump forward to this guy. Let's jump forward to some trig derivatives. We've done examples using trigonometry, but let's just get to these. So the derivative of the sine of x is equal to the cosine of x. Nice. And the derivative of the cosine of x, I know we all want to say that it's sine of x, and you're right, but it's the negative sine of x. Okay. So I'm going to skip the proof on this one, just in the name of time, but this is one that is not hard to prove. It just takes a little bit of the proof you can work out on your own. It's not one that's hard to prove. You do need to know a little bit about sum of angle identities that'll come up in the proof. So let me just make a note of that. It will use the sum of angles identity. Okay, and so what, if you recall, that sine of alpha plus theta is equal to sine of alpha cosine of theta plus cosine of alpha sine of theta. So that'll come up in the proof. All right, but otherwise it's a totally straightforward application of the definition. All right. So we can differentiate trig functions now, that is certainly the ones that involve sine and cosine. Let's do an example or two. Okay, let's say we want to differentiate f of x equals 2 times the sine of x. It couldn't be easier, right? So f prime of x is equal to d dx of 2 sine x. And of course, again, I'm being very deliberate with my notation here. And that would be 2 times the cosine of x. That's what we just saw, isn't it? Okay, now a problem like this, you might be able to start here and just jump right to the end. You might be able to look at that and say, oh, I see exactly how this is going to go. No problem. How about another example? Let's say g of x equals sine of x over 2. Okay, so again, this one is very straightforward, hopefully. G prime of x equals 1/2 d dx sine x. All right, so that's 1/2 cosine of x, isn't it? All right. How about this guy? Let's say y is equal to x plus cos x. Okay, so we've got multiple terms added together. So then dy dx is equal to, and you can break this apart right up front if you want to. You could say it's d dx of x plus d dx of cos x. All right, so you can pull that sum apart, work out each of these individually. This derivative is 1. This derivative is negative sine x. Right, and so you would say it's 1 minus the sine of x. Okay, very good. So I think I'll break the video there, and we'll come back and do some more examples in a moment, in the next video.